Welcome to the BareMetal. So far we have played with the raw atoms of computation. Integers, floats, booleans and cars. They are fast but lonely. To build a blazing fast BareMetal apps, individual atoms just aren't enough. Think about it. You can't build a skyscraper one brick at a time. You need structure. Today we fuse these primitive types together into a massive predictable blocks of memory. Welcome to the compound types. Let's see what we're gonna learn today. First, we'll force tuples to pack mismatched data into unbreakable cargo boxes. Then we'll build arrays to align uniform data directly onto the stack. Pure Ironclad control. So without any further delay, let's get into it. Look at these raw scalars drifting in our workspace. An integer, a float, a car, completely isolated. But the second we slam them into a heavy bracket, shut, boom, we crush that empty space and forge our first compound type. First up, the tuple. Think of a tuple as a heavy-duty, fixed-length cargo box. Once you forge it, it cannot grow or shrink, but it's superpower. It doesn't care about uniformity. You can pack an integer, a float and a byte side by side in a perfect harmony. So where do we actually use this? Everywhere. Need to track an XYZ coordinate in 3D space? That's tuple. Returning an RGB color value to paint a pixel on the screen? Tuple. It's the ultimate tool for grouping related but distinct piece of data into a single identity. But how do we get the data back out? Direct access. By using a period followed by the index, we can surgically extract exactly what we need. And remember, Rust is a system language, so we always count from 0. Index 0, 1, 2. Want everything at once? You can shatter the tuple using pattern matching. This is called destructuring. In one clean line of code, we burst the compound element open and bind its internal guts to 3 brand new distinct variables: clean, fast and elegant. Before we move on, meet the ghost of the tuple family, the unit type. It's an empty tuple with no values. It represents nothing, takes up absolutely zero memory and is what Rust expression quietly returns when they have nothing else to give. If tuples are mixed bags, arrays are strict military formation. In an array, every single element must be exactly of same data type, no exceptions. Try to slip a float into an integer array and the compiler will mercilessly strike it down. Why use an array? And the answer is performance. Because arrays have a fixed length, Rust allocates them directly onto the stack, a blazing fast, highly organized section of memory. It's a single contiguous chunk of data, purely hardware efficiency. You can lock down the type explicitly by defining the data type and the exact length separated by a semicolon. And if you need to initialize a massive array with the exact same value, use the shorthand. Give it value, a semicolon and the count, boom, instantly populated. When do you use them? Whenever the data size is universal constant, the days of the week, the months of the year, or a fixed size network buffer. If the size will never change, an array is the best friend. If you need it to grow, you'll need a vector, but we'll tackle those later. Accessing data is standard. We use square brackets and the index. We want the first element, we target index 0. The hardware jumps straight to the exact memory address and pulls the value, fast and frictionless. But what happens if you ask for index 10 in an array of size 5? Maybe the user inputs a bad number. The hardware doesn't know any better. It's just going to try and read whatever the garbage value lives at that memory address. In languages like C, it lets you do it. It reads the corrupted memory and your program gets hacked or behaves unpredictable. But Rust slams the blast doors shut. It checks the bound at runtime. If you step out of the line, it refuses to execute. It panics. For many of you, a panic sounds scary, but it is your ultimate protector. Rust would rather intentionally crash your program immediately than allow it to silently corrupt your memory or leak secure data. It is memory safety guaranteed at the hardware level. So there you have it. Tuples for fixed size, mixed type groupings. Arrays for fixed size, uniform performance on the stack. Two vastly different structures, but both giving you absolute authority over how your data is packed. Next up, we dive into functions, control flow and how to actually make these data types move. Drop a like, hit subscribe and join the crew. And stay close to the metal. BareMetal out.